I will give several definitions of algebraic dimension of a variety or of a ring, in fact, and then they will be for algebraic varieties. These definitions are equivalent, and then next time we shall use it for different purposes. Okay, so the first definition is something which we already sort of have. For every field K, you can find a transcendence basis in this field. So it's an extension of K small, and you take T1 to Tn are algebraically independent elements in K. They're algebraically independent over K small. This is the first. And the second, that K over the field of rational functions is algebraic. In other words, this is equivalent to having for each x in K is algebraic over this field of rational functions. That is, it generates a finitely dimensional ring over the ring of rational functions. Then n is called transcendence degree. This is for all fields, but if, for instance, K is a a field of fractions, of rational functions on X algebraic variety, say affine variety, then n is called algebraic dimension of X. Okay, and this is something which we used already, because when we spoke about the Noether lemma, we proved the following result. Proposition. Let X be a affine variety. N is equal to A of X. Then there exists finite dominant map from X to Cn. So this already has a geometric interpretation. I'm now going to explain that if you have a divisor inside the variety, then its algebraic dimension is dimension of variety minus 1. Well, I'm going to do it only for divisors in Cn. But it's generally true, and the same argument will work. Except that it will be slightly more troublesome, because there's a distinction between principal divisors and divisors. So what is a divisor? Suppose you have a function, you have a affine variety and a function. You have a function f, and the corresponding ideal, it's a principal ideal generated by f. Then you can consider the set of all v of f, this common zeros, the zero set of f. Sort of clear to sort of obvious that a function is common zero of this principal ideal if and only if f vanishes in that point. And then I'll consider the irreducible decomposition. Vf is union of di, irreducible decomposition. Then di are called divisors. This is slightly unpleasant because you need to use this irreducible decomposition. So, but on CN it's much better. So we have this lemma. Yeah, and this is called principal divisor. And VF, principal divisor. And now we have this lemma, which uses factoriality. In fact, it's true for all factorial rings. On Cn, all divisors are principal. In other words, if you have this decomposition, then each of these components is itself a zero set of some other function. So proof. Suppose you have f in this polynomial ring. You have its irreducible decomposition. So it's, we use the Gauss lemma and factoriality of this ring, and and prove that all divisors are principal.
What is divisor? We define the
It's a irreducible component of a principal divisor. Principal divisor is zero set of a function. It is false outside of Cn. It's not hard to see even for in dimension 1. You might have, so in dimension 1, if your variety has dimension 1, the ideals, divisors are points. But it can be, it can happen that all functions have several zeros. There are no functions which has only one zero. And of course, the divisors are points, and principal divisors are zero set of functions. So it might happen that you have, even on dimension 1, it might happen that you have a divisor which is not principal in that situation. So it will be a point, but there are no functions which vanish on this point.
But now it looks like there is nothing to prove because there is a reducible component, there is one-to-one correspondence with
This is what this.
Decomposition of the polynomial.
Yeah, of course. It's very elementary. Thanks. Yeah, fi power alpha I. Then this is true for any function, and this gives you the zero set of f is a union of zero set of fi. But since this ideal Fi is prime. This is prime because the Fi are prime, indecomposable. Fi is prime, so this corresponding divisor is already reducible. So in other words, every divisor is a union of reducible divisors which are all principal. This is what we need to show. All divisors are union of principal irreducible. And then you can split them further. This is an artifact of having factoriality in your ring. Okay. And I will use this to find dimension. So this is something I will be using. Proposition 1. You have D in Cn, irreducible divisor. Then algebraic dimension of this D, of this divisor, is n minus 1. Yeah, it's also not hard. Okay, so let's prove it. We have D is by this argument a zero set of F, where F is prime, irreducible polynomial. Okay, it might happen that so we have T1 Tn coordinates on Cn. Now what can happen is that this polynomial is independent on some of these variables. Okay, it can't be independent on all of the variables because then it is constant. So I will renumber the variables in such a way that assume that f depends non-trivially on Tn. Otherwise, I would just renumber. Now consider Tn restriction to D as an element in K of D. It is a root. So I defined algebraic dimension as transcendence degree of a ring of regular, of a field of rational functions on a variety. And then I proved that all divisors in Cn are union of irreducible are principal. So all divisors on Cn are union of irreducible components, and all these irreducible components are principal divisors. They are given by varieties, by equations. Each divisor each irreducible divisor in Cn is given by polynomial equation. And now I'm proving that algebraic dimension of a divisor is n minus 1 if it is divisor in Cn. Okay, I write equation of D. It exists as we proved. This is because the ring of polynomial is factorial. So every equation can be decomposed into a product of irreducible polynomials. Then you have coordinates, and the function f, I assume that depends non-trivially on Tn. It depends on non-trivially on some coordinates, so I will be numbers that it depends non-trivial on Tn, and then I consider Tn as a function on D, and it is a root of a polynomial P of T equals 0, where which belongs to O of well, to polynomial ring, to rational functions on T1 dot Tn minus 1, and then polynomial on the last variable. This is because you have a polynomial relation between the first n minus 1 and Tn, which is non-trivial in the last variable, so degree of P is positive. Okay, and this implies that Tn is restricted to D is algebraic. Algebraic over this ring, this field of rational functions on T1 dot Tn minus 1. And of course, this implies that then K of D is algebraic extension, actually finite extension of C T1 dot Tn minus 1. So, and then this implies that, of course, that A of D is less than or equal, right, than n minus 1. We want to opposite inequality, and then we're done. Yeah, but on the other hand, K of D contains this ring field of rational functions This is because each of these functions is non-trivial on this divisor, because this is, I mean, this K of D contains a field which is C T1 to Tn quotient by these polynomial equations, P of T equals 0, or just by ideal generated by P of, here you have T, here you have quotient by the ideal generated by P of T, and this is a field. This is a field, a finite field extension of this field, so it's contained there because of this argument. Is it clear? In other words, how we obtain this ring of regular functions on divisor? We obtain it by taking a quotient. So by definition of D, the regular functions, is C is polynomials T1 dot Tn quotient by the ideal generated by F. And then this implies that, because this is what happens with this. So P of T after so O of D localized in C in all non-zero polynomials on the first n minus 1 variables. This gives you rational functions. And quotient by rational functions of T1, of course, Tn minus 1. we didn't localize on the last function, so it is this, and the quotients by f. But this is the same as the quotient by p of t n minus 1. Oh, yeah, tn. This is tn, of course. The last variable which we didn't hear here is tn. Okay. And this is a finite extension of this field, so it contains this field. And this implies that A of D is at least n minus 1. We are done. Okay. Questions, comments? Is it clear?
Question. So why this inclusion of fields respects the definition of dimension? So if we have a transcendence basis.
This is a transcendent basis.
Yeah.
And this finite extension.
Okay.
So you obtain that your rational functions on a divisor are finite. What happened? Your rational functions on divisor is finite extension of the field of rational functions. By this, you just write it explicitly this way.
And in general, if we have an inclusion of two fields, not necessarily finite, then that respect is.
Yeah, you can choose a transcendence basis first in your first field and then in the second. So it would be indeed, there would be such inequality, except that we didn't prove that this is well defined in the following sense. Suppose I have two transcendence bases. Then a priori they can be different. In fact, in the end of this lecture, you will see that it can't happen a posteriori after we prove the equality of dimensions. But so far, it is possible to show, but it would be hard. So you can do it like using Galois theory and this stuff. But I don't do it, and I don't pretend to do it. I can leave it as an exercise, but in fact, it's easier to define another dimension, which is called cool dimension, show that it is correctly defined, and then it is equal to this dimension a posteriori. Okay, so this is the other dimension which I'm going to use. In the end, it will be equivalent to that dimension. So this is a nice notion which is quite suited for all these arguments. So consider a chain of prime ideals. So I have let 0, which sits but not equal to in P1, which sits but not equal properly in P2, and so on, Pn, and then it sits but not equal to A. The maximal n, such that this is true, such chain exists. So Pi are principal ideals, oh sorry, prime ideals in A. So the maximal n such that such chain exists is called Krull dimension. So let me give you example. Example 1. So if A is a field, Krull dimension is equal to 0. This is because we can't have P1. There's only zero. This is the only prime ideal. Another example. Dimension of Z is equal 1. This is because Z is a principal ideal ring, which means that every ideal is generated by a irreducible by a prime number. Every prime ideal is either 0 generated by prime number. So you have 0 sits in a prime number, but then it can't be contained in any other ideal because the quotient by the ideal generated by prime number is a field. So prime numbers generate maximal ideals. And the same is true for all principal ideal rings. If A is principal ideal, then dimension of A is no more than 1 for the same reason. Because if you have an ideal generated by P, it sits in some other ideal, it is impossible. This other ideal can be prime because it, yeah. P is irreducible, so it cannot sit in smaller ideal. Okay, and this includes polynomials. So the ring of polynomials has Krull dimension 1 for this, which is something. But in fact, you will see that every polynomial ring has the same dimension as the number of number of variables. So K of T has Krull dimension 1 because it's principal. K of T1, T2 has Krull dimension 2, and so on. Okay, and in the end here I will prove that algebraic dimension is the same as Krull dimension, at least for affine varieties. Comments, questions? So I think the next is again a picture of Krull in Brazil.
Is it straightforward to prove that the dimension of polynomial ring is respect to
No. In fact, it uses. Well, yeah, it's not straightforward. It uses this theorem which I'm going to prove, this one. Because algebraic dimension, no. It's not well defined, but Krull dimension is well defined, and they're equal. So this is how you prove that algebraic dimension is defined uniquely independent on the basis. Yeah, and this is Krull, in fact, is Brazil. It's a year before he died, I think. 2 years. He had some Brazilian students, including, of course, our colleague Storr. Okay. And now I'm reminding you a bit about the it's something which we already had before. But I will use it a lot today. So definition. Suppose you have a ring A. A ring is called local. If A has only one maximal ideal. If A has only one maximal ideal. The idea is that local rings are rings of germs of functions. This is something we discussed. And this is why they're called local. It's they represent the geometry of a neighborhood of a point. And the second definition, suppose I have P as a prime ideal. And S, a prime ideal in A. And S is A without P. This set is multiplicative. If two elements don't belong to P, their product doesn't belong to P, so you can take a localization. A localized in S is called localization of A in P. And there is a trivial observation that this localization is actually a local ring. We already had it before. So, claim AP. So this is denoted by AP is local. Indeed, all elements X not in P are well P times over AP. So I extend I extend P to this localization, and all these elements are invertible. And this means that if an ideal, well, this implies that every ideal is contained in P. In AP belongs to P tensor over AP. This thing is usually denoted by P. So it's a sloppy language. It's abuse of a language, but it is what people use always. And this implies, of course, that P is maximal. So you can produce maximal ideals from localizations. Okay, and Nakayama tells us that if you have M maximal ideal in a local ring, and you have M is finitely generated A model, then M quotient by the maximal ideal times M is never 0. And the proof, this is because 1 plus M small to the maximal ideal times M big is M big. But this is invertible. Okay. Now we'll use this to have finite extensions and prime ideals. There are two lemmas I'm going to use to prove now. They're similar. So the idea is you have, in both cases, you have B contain A is finite over A, so it's finite as A model. Then every prime ideal in A can be is obtained. First, every prime ideal in B gives you a prime ideal in A. Non-zero gives non-zero ideal, and conversely, every prime ideal in A can be obtained as intersection of a prime ideal in B with A. So there's correspondence between ideals in B and ideals in A. So the first lemma I'm going to prove is this lemma 1. which says that the restriction is non-zero. So lemma 1, you have B contained A is finite. You have a non-zero ideal, P inside B non-zero ideal. You take P intersected with A, then this intersection is non-zero. It's obviously prime. But that it is non-zero, it's not that obvious. So proof. It's still simple. So you do, first you do a localization. Oh, sorry, it was Q here. So we define this as P and this is Q. So we localize A in the complement to P. So AP is A localized in A without P. This is well defined. And then you can consider B localized in the same set. A minus P minus 1. It's a finite over AP. I mean, you take something finite extension and you localize this everything over some multiplicative set. This gives you it's still finite because it's finally generated. The same generators will generate this localization. Okay. Then you have B. Do I have an notation for that? Yeah, it's called BP. So you have BP contains AP, finite, and then take a quotient by P. It will be finite over AP quotient by P. So what does it mean quotient by P? This means that you take P and tensor multiplied by B. And consider this gives you an ideal. This is something we did a lot. We always use the observation that M times A quotient by P is equal to M quotient by P by P, well, by PM. So this is what we do here. And this is a field. And this has no zero divisors because, well, it doesn't matter if it has no, sorry, it might have, I'm sorry, of course it might have zero divisors. What it definitely doesn't have is nilpotence. Well, never mind. Even if it has nilpotence, it still doesn't matter because this is finite algebra over a field. And this means that it contains a maximal ideal, finite number of maximal ideal. Maximal ideals. Yeah, so I'm doing the second lemma, sorry. This lemma is, which I didn't even write. The second lemma says that if you have an ideal NA, you can always lift it to B, and here we're starting with ideal B, we want to obtain an ideal NA. So suppose this ideal is 0, then your ideal P is 0, then AP is a field. So we assume that P is 0 here. BP is finite, just finite algebra over a field, and guess I have to erase something. So if P is equal 0, P is equal 0, then AP is a field. BP is finite, is Artinian algebra over a field. And this means that it is, well, it's also has no, it's a localization of something which has no zero divisors, so it has no zero divisors. It is a direct, it's a field. No zero divisors. Finite over a field, then BP is a field, and this means that it has no non-zero ideals, but Q is non-zero ideal. Non-zero ideal, which is contradiction. Why Q is non-zero ideal? Because you can localize over Q. And localization over Q contains BP. It's a bigger localization. You localize over bigger number of, you invert bigger number of elements. In case of BP, you invert all elements which are in A but not in P. But if you localize over Q, you would localize over all elements which are in B and not in Q. It's a bigger set. So you obtain a contradiction because you obtain that this Q, which is an ideal, it can't be an ideal because this is a field. Okay, so this was this lemma 1. Now lemma 2. Was it clear? So somehow I gave you half of the proof of lemma 2 as well on the way. I can repeat avoiding this. So again, we have B. Inside you have ideal Q. You have A. Inside you have ideal P. If P is equal 0, we need to show that P is non-zero. If P is equal 0, then AP is a field. If P is equal 0, AP is a field. And BP, which is localization over the same set, is, is a finite extension. So it's also a field. And this is impossible because it contains Q. Cannot be. Okay, so this is how I prove this lemma 1. Sorry? Q is given as non-zero ideal.
So you just consider the one case?
Yeah, Q in B is non-zero prime ideal, then its intersection with A is non-zero ideal. Okay. Any other questions? Now lemma 2, which is just symmetric statement. again you have B contain A finite over A. So it's finite as a model, finitely generated as a model. You have prime ideal now in P and A. P in A prime. Then there exists a finite number, but non-zero number, positive number, of number of ideals Qi in B such that prime ideals such that Qi intersected with A is equal to P. So every ideal in A can be obtained from B, and there are finitely many ways of doing it. Okay. And the proof is pretty much the same. So proof. We consider AP is localization of A in P, and BP is B multiplied over A with AP, so this is the same localization over the same thing. Yeah. And then you have a map, natural embedding from A, natural map from A to AP over P. So a map from A to AP is an embedding, and then take a quotient. Its kernel of this map is P, which is sort of clear because this to that is embedding, and here we take a quotient over all integer elements which belong to P. For instance, AP quotient by AP quotient by P, it's just an embedding. This is a ring without the divisors, and this is its fraction field. And you have A mapped to there. Its kernel is obviously P. And this is a composition of these two maps. This was step one. And this is the statement of step one, that the kernel of this natural map is P. So step two, we know that BP quotient by P is non-zero. This is because BP is finitely generated model over AP. And we apply Nakayama lemma, which is there, which tells us precisely that a finitely generated model cannot be equal to maximum ideal time itself. Clear? Questions? Should I repeat something? Yeah, so step one is that we have this map from A to its localization, from A to quotient by P to localization quotient by P, and the kernel is P, just from this sequence. And the second statement, we go to BP, this one. And I claim that BP is quotient by P is non-zero. This is because of Nakayama lemma. Nakayama lemma tells us that if you take a finitely generated model, quotient by maximal ideal of a focal ring, this is never zero, unless the model is zero, of course. But B is non-zero, so this is non-zero as well. And this is zero. I mean, then the KM lemma tells us that it's never 0. Okay, but then BP quotient by P is equal to A to BP tensor over A by P. It's a finite algebra over a field AP quotient by P. Finite dimensional. So it's Artinian. And then it means that it has finitely many then this quotient, BP over P, has finite number of prime ideals. All maximum ideals, in that case, it's the same. So we denote them Q1 dot 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 Qn, or Q tilde, Q bar. Q1 dot Qn, maximal ideals or prime ideals in BP quotient by P. So it's an Artinian algebra which contains this field. So it's non-zero. Okay, and now we have Q1 dot dot Qn. It's pre-image of Q1 bar dot dot Qn bar in B. They're also prime ideals. But then what will happen if you take Q intersected with A? I claim that it will Qi intersected with A is P. This finishes the argument, obviously. We found an ideal, and in fact, this is equivalent. So it will be this Qi will be precisely the ideals in B which have this property. Okay, and the argument is sort of trivial. So we have Qi, because Qi intersected with A is mapped to 0 under a map A goes to A quotient by P, or a P quotient by P. This is because it contains P. So this intersection, it belongs to AP, and the kernel of the map from AP to AP quotient by P is precisely P. So this is P. And the converse is also true. If you have an ideal which is mapped, which is pre-image of an ideal such that its intersection with A. So if you have an ideal in BP quotient by P, which intersects with any ideal in here, if you take its pre-image and you intersect with A, it gives you P if and only if, this if and only if condition. So if you have an ideal in, if you have an ideal Q in B such that this, which is mapped to an prime ideal in this quotient, then you can intersect this ideal with AP, and it will be an ideal which is mapped to 0 under the quotient by P. So by this step 1, this means precisely that this ideal intersected with AP is P. And this is what we need. Now we take its preimage from BP quotient by P to B, and we obtain an ideal in B which gives you P after intersection with A. Just follows because of localization. And of course because of this trivial observation. Okay. Should I repeat it, or is it clear? Not that clear? Okay, so what is our step 2? First, we consider this ring. It's finite over a field. It's finite AP quotient by P. This means that it has finite number of prime ideals. They are maximal as well. It's the same for this finite dimensional, for Artinian algebra. We know pretty much everything about Artinian algebras. So we take our ideals, Q1 dot Qn in this BP quotient by P. We take their preimages to B. Now I claim that these ideals intersected with A are equal to P. This is because we have this projection. B goes to BP, goes to B, P quotient by P. Here you have A, goes to AP, goes to AP quotient by P. And the kernel of this map, kernel of this composition we denote by psi, and we know that kernel of psi is P. So now we have Q here, Qi in B. You intersect it with A, and it becomes kernel of psi. This means that Qi intersected with A is precisely P, because kernel of psi is P. This is what is done in step 2. And of course, conversely, if you have an ideal in B which intersects with, you have an ideal Q which gives you P after intersection with A, this is precisely the same as an ideal in this quotient. And you can even localize over this ideal, and this would give you there are as many ideals which have this property as there are ideals in BP. Because every ideal Q which intersects with give you P, it will give you an ideal in there, and converse is also true. I mean, if you have an ideal, you can always, a prime ideal, you can always localize over things which don't belong to it. And it's, okay. I can repeat it again. Still unclear? Okay, it's a sort of easy argument if you just think of what happens if you take, like, you have a chain of ideals, you can take subsequent quotients, and these subsequent quotients produce you some Artinian algebra, and then you can leave them and do whatever you like with them. So in the end, we obtain this nice theorem, which somehow IT McDonald don't name this theorem, so I didn't even know that it's Cohen-Zeidenberg, but now I know. They just call it lift and pull back and push forward of prime ideals.
Goes up, goes down.
Yeah, goes up and goes down theorem. Okay, so theorem. So you have a B containing A, a finite Noetherian over A Noetherian. I will, for simplicity, I will assume they have no zero divisors. You can prove it with zero divisors as well. I just don't want to. Then you have a chain of prime ideals. Q1 sits not equal in Q2, not equal in Q3, and this is not equal to 0, and in the end it's not equal to B. Chain of prime ideals. And then we consider by Pi the ideal Pi intersected with A. It's Qi intersected with A. It's clearly prime. And then, first observation that this chain is they're all distinct. So you have P1, 0 is not equal to P1, not to P1 is not equal to P2, and so on. They're all not equal to up to Pn, which is not equal to A. And the second is every chain Pi of ideals in A can be obtained this way. This is very similar, in fact, to, and lemma 2 is this is similar to lemma 2. It is also similar to the result which we had, that if you have a finite map, it's always surjective. Surjectivity is lemma 1. Oh, no, it's both lemma 2. So it's always surjective and has finite number of, every point has finite number of preimages, non-zero finite number of preimages. If you think about pointers of prime ideals, then the preimages is precisely intersections, and sorry, the image of ideal in B is an ideal, is intersection with A. And what this theorem says is that if you have an ideal in A, it has you have finitely many ideals in B, which are mapped to this ideal. And here you have the same, but with chains of ideals, which if you think of Zariski topology, they're just chains of points with funny property that each point contains the next point in its closure. But if you don't care about Zariski topology, just look at this as a particular property of chains of ideals. Okay. And the proof is very simple. It immediately follows from lemma 1 and lemma 2. So proof of 1. We apply, use induction, and we can apply, always can apply this lemma 1 to a quotient by so suppose that pi is equal to pi minus 1. Suppose that pi is equal to pi minus 1. We replace a by a quotient by p I minus 1 and b by b quotient by q I minus 1. Then you have a non-zero. This again, this ring is finite type of that. Is finitely generated as a quotient by pi minus 1 model. So this replacement makes sense, and then after that, it remains only to show that P1, which is intersection of the first ideal with A, is non-zero. So it remains to show that Pi quotient by Pi minus 1 is non-zero in A quotient by Pi minus 1. And this is precisely lemma 1. So lemma 1 tells us that if you have B and you have Q1 sitting in B, non-zero, you intersect Q1 with A, and this is non-zero. Here your P1 becomes Pi by Pi minus 1. It is non-zero if Qi by Qi minus 1 is non-zero, which is given. So it can't be 0. Okay. So this is the first statement. It's about distinct chains of prime ideals remain distinct. Now we have to, this is, you intersect chains of ideals with A, and they become non-trivial chains of ideals. Now we need to prove converse. So this is the proof of statement 2. Okay, so lemma 1 is no longer needed, I can erase it. And proof of 2 is again inductive step by step. I think I'm over time slightly. Not slightly, but a lot, sorry. Yeah, let's have a break now. Temos intervalo para 5 minutos. Agora. was going to tell how you prove the second statement of the theorem, namely how you lift. You have a chain of ideals in a smaller ring. You want to obtain a chain of ideals in a bigger ring. So you do it by induction. Of course, you can just put an ideal down, and you can you know that every prime ideal in the quotient ring gives you this by this lemma 2. Sorry, every ideal in a smaller ring gives you an ideal in a bigger ring. Find the many of them. But it's not enough because we want this ideal to be included in each other, and still it's very simple. So suppose you have P1 0 not equal to P1, not equal to P2, and so on in A. And then you have Qi, Q1, up to Qi in B, such that Qi intersected with A is Pi. So we already have found lots of ideals. We need to find the next ideal. So we need to find Qi plus 1. And we do it as follows. We take Qi plus 1 in P quotient by Qi. This is finite over A quotient by Pi. This is because Qi intersected with A is Pi, so this is a finitely generated model over this ring. This ring is actually without zero divisors, and this one as well. They are all, because these ideals are prime. So the assumptions of lemma 2 are satisfied. It says A, B, no zero divisors. So anyway. And then this means that there exists, so you have an ideal, we need this ideal, but we have an ideal Pi plus 1 inside A, and by applying lemma 2, you find an ideal in A by Pi. You find an ideal Qi plus 1 in with bar, this is with bars, in B quotient by Qi, and you take pull preimage of this ideal in B. This will be an ideal which precisely has this property that intersected with AI, it gives you, with A, it gives you Pi plus 1 by construction. Am I clear? So we just take, instead of taking ideals in A and B, we take them in quotients. We take in successive quotients, and we take this gives us this flag of ideals which we need. Okay. Good. So this is, the story is the following. So before Zariski came to Harvard, he was a professor in Johns Hopkins, and he had several very good students there, which include Cohen and Zeidenberg, who were students at more or less the same year, I think. Zeidenberg was 1 year older, but completed his degree 1 year later than Cohen. And then they did this paper together, and then Zeidenberg lived until 88, and he was professor in Berkeley and did a lot. And Cohen unfortunately committed suicide in 55 because he believed his mathematical ability decreases, and he didn't like what he was doing. So Zariski was very sad because they were collaborating at the moment.
Is it the same Cohen Macaulay?
Yeah. Yeah. He did lots of very interesting things in commutative algebra, like Zariski. Okay. Now, but then he switched to abstract algebra. He did some interesting things with even Kaplansky and some other as well, but then he died. And I couldn't even find his picture. It's not in internet, so this is the best picture you have. It's his grave, which is a pity. Okay, we have a corollary, which is really simple about crude dimension. It immediately follows from this theorem on going back and down and up with ideals. So corollary. Suppose you have A to B is finite ring homomorphism, and finite and also dominant. Then dominant we want because we want that one of them to be contained in another. This is part of our assumption. Then a dimension of A is dimension of B. And the proof is clear. There's nothing to prove because if you have a chain of ideals upstairs, you have it downstairs. If you have it downstairs, you have it upstairs. And there's, its length is the same in all these cases. So there's pretty much nothing to prove. Am I clear?
What is?
Why do you use?
Yeah.
Oh,
Why do you use finiteness?
Because this theorem uses finite. It's false without finiteness. I mean, we have the standard example of something which is not finite, which is you have. Okay. Julia? Okay. Yeah. So this is definitely false when you have things like. First, you might have things like C2 over C1. This is not finite over C. Like this projection, it's clearly not finite and the dimension is different. But this is because, I mean, if you have an ideal there, it doesn't necessarily come from there. You don't have lifting. So you can't expect that you have finitely many preimages of every prime ideal. Okay. Yeah, now I promised you this theorem. I can prove it now. That whole dimension is algebraic dimension. So theorem. So this, we can prove it in more general situation, but it becomes more and more awkward to state. So I just stated for finitely generated rings, and you can try to generalize it for bigger generality. So the point is, it's obviously false. For instance, if you take B, it's obviously false if you take the ring A of just rational functions, C of t, and so B is C of t and AC. B of C of t. So it's it has only one ideal. Its Krull dimension is 0, but its transience degree over C is 1. So you have to state it for varieties. suppose X is algebraic variety, affine variety. You take Krull dimension of, then Krull dimension of OX is equal to A of X. This algebraic dimension of this variety. So I am avoiding saying algebraic dimension of a ring because it makes no sense. It depends on the base field, on this kind of things. Unlike Krull dimension, which is very universal, algebraic dimension is better to define for varieties. Okay, so step one is you can always replace. So step one. So we replace, consider finite dominant map from X to Cn. It exists by natural lemma, but then the algebraic dimension of these two objects is the same because it's finite extension of the corresponding fields, and we know that transience degree under finite extension doesn't change. It's very easy. And then the Krull dimension also doesn't change. So remains to show, since Krull of X is equal to Krull of Cn, and A of X is equal to A of Cn, it remains to show only that A of Cn is equal to dim to Krull of Cn.
Krull dimension doesn't change because of the
Yeah, of this corollary. Okay. So now we have step two, which tells us that if you have a maximal chain, if you have non-maximal chain ideals, it makes no sense. So where Krull dimension, it computes the maximal length, maximal length of maximal chain of ideal. But then, if you have a non-principal ideal, so step two, if P inside O of Cn is so I'm interested in the smallest possible. I want an ideal which starts as chain. It's not maximal, it's a minimal principal ideal. Is a minimal principal ideal is minimal prime. It is principal. Well, this is because it is divisor. I mean, every so it is if you have any ideal, it contains some irreducible element, some irreducible polynomial, and then the corresponding ideal is even generated by this polynomial is even smaller. Because otherwise P contains the ideal generated by F contains 0. And this is proper. So you take any element, you decompose it into irreducible components, and one of these irreducible components definitely is contained in P, because the product of things which are not contained in P cannot belong to P. So this means that P contains a single irreducible, at least one irreducible polynomial. And it gives you a principal ideal which is intermediate. So the first ideal in this chain, in the maximal chain, is always principal ideal. Okay. We're almost there. So I guess this can be raised now. So we have a divisor D. We have a chain of ideals. So step 3. We have a chain of ideals 0 belongs to P1, belongs to P2. This is all proper chain. And P1 is ideal of a divisor D. D is irreducible divisor, like prime irreducible divisor in Cn. Yeah, there was this, we know that A of D is n minus 1. This is something we had, it's called proposition 1. We have already discussed that if you have a divisor somewhere, like in Cn, then its algebraic dimension is n minus 1. On the other hand, the Krull dimension of D is also n minus 1. This is because you have your shortest chain of ideals. It starts with P1. But then if you take the quotient by P1, it will give you a shortest chain of ideals for O of D, for the ring of regular functions in D. So because of Cn quotient by P1 inside of P2 of Cn quotient by P1 and so on, this is a chain, is a maximal chain in O of D. So this chain, let me write it here. So because O of D is O of Cn quotient by P1 and 0 inside O of D quotient by P2, you have P2 times O of D. Here you have P3 times O of D, and so on, is a maximal chain for O of D. If you have a bigger chain, then you would obtain a bigger chain for Cn. But we already have a maximal chain. So this gives you the length of the maximal chain of D, which is n minus 1 by construction. Okay, now let's use induction on dimension. Using induction on A of x or dim of x, we already obtain that dimension of D is equal to algebraic dimension of D. And this is equal to yeah. And then dimension of Cn is dimension of D plus 1. This is proven here. And algebraic dimension of Cn is algebraic dimension of D plus 1 by proposition 1. Okay, so we're done. And now this gives you that the dimension is well defined. Because you can always pass to crude dimension, which is well defined because it's a maximal length. Okay. I suppose it could be a direct way of doing it. And in fact, I think sort of remember that it's maybe even given in van der Waerden. But here it's sort of more straightforward anyway, even if it's not. Okay, so this is more or less it. But before I finish, let me give you, explain the proof of Hilbert-Nurstein and Zatz. So we started the whole set of lectures with Hilbert-Nurstein and Zatz, which was proven using some set theory. And of course, nobody would really like it because, I mean, we're doing algebraic geometry, not set theory. And the canonical way of proving Hilbert-Nurstein and Zatz starts here. So you have to do whatever, everything that I did without ever mentioning Hilbert-Nurstein and Zatz and algebraic geometry. Just do the commutative algebra, which is not that hard. It's slightly more boring, but it's still very easily doable. And you arrive at the point where kind of deduce Hilbert-Nurstein and Zatz. If you remember, it's proven. So Hilbert-Nurstein and Zatz is deduced from the following proposition. Suppose you have F a field which is finitely generated as a ring over our C or our algebraic closed field. Then finally generated as an algebra. Then F is K. How you prove it? Okay, you found a maximal ideal. Maximal ideal exists. Then you want to show that this maximal ideal gives you a function with values in K bar. But if F is the quotient by the maximal ideal is K bar, this gives you this function. So this is the only thing which you need to prove Hilbert-Nurstein and Zatz. Okay. And now we have, if Noether lemma implies this proposition because, okay, so you have this finitely generated algebra. What is its dimension? Okay, it has no ideals. It's a field. So dimension of this F is 0. Its clear dimension is 0. It has no ideals. But then its algebraic dimension of this thing, it's finitely generated algebra, so the algebraic dimension makes sense, is 0. And this means that A is algebraic extension of K bar. key bar. But key bar is algebraically closed. All its algebraic extensions are trivial. This implies that f is key bar. So this is the canonical way of doing Hilbert-Neustadt's ansatz. Okay, now I'm definitely done. Thank you very much. Muito obrigado.